So welcome back. What I'd like to do in this video is to talk about another type of recommender system, which is the dimensionality reduction approach. So the way I think about recommenders is that there's broad types. We've talked about non-personalized recommenders, so popular, recent, maybe random. We've talked about different personalized versions, so content-based filtering uses known information about the items. For example, we could be using tag information that this item is yogurt, or this movie has Steven Spielberg as the director. So we're using attributes that were known and we can agree about the movie to make recommendations. Then we moved on, we talked about collaborative filtering, where we had methods like user-based and item-based collaborative filtering that are based on neighbors. There are a few other major approaches to finding recommendations. So one of them is this dimensionality reduction approach. The basic idea here is that the observed ratings that we have tend to overfit tastes. The way I like to think about this is usually when we do machine learning, if we observe something, that something is a function of two things. It's a function of the signal and the noise. Back in Machine Learning 1, we called these irreducible errors. These are just purely idiosyncratic factors that explain why, as opposed to these signals. So this is the signal, this is the noise. And I think of ratings as being the same thing. So my rating, so make this an R instead of a Y, my rating of some movie will be a function of things that are predictable. So I told you I like funny movies, and if it's a funny movie that isn't stupid, chances are I like it. So that would be an example of something that is very much signal. But then there's going to be other things that you probably can't explain. Why do I can't even explain why I like certain movies. And there's just something idiosyncratic about it that I happen to like it, even though you wouldn't think I would. Same is going to be true with music and lots of other categories. So the point is, the observed rating, so those are like my Y's in machine learning, overfit. So they have the signal, but they also have this irreducible, idiosyncratic error mixed in with them. What we'd like to do is to produce a more compact representation of my tastes. So think of that as your X's. So these things that are going to explain why I like movies. So it's kind of simple to say I like comedies, but what if there are other things that make up my taste in movies that would explain why I like certain movies and dislike other movies? So what we're going to try to do is identify these. Now, you could think of content-based filtering as having done that with an item profile. But the difference between content-based filtering and these dimensionality reduction methods is that with content-based filtering, we were explaining your tastes based on attributes that we could agree on, like the director and the genre and the year it was made. But what if my tastes are more latent? So you can't really put your finger on, well, it's funny, or it's by a certain director that I like. What if these more latent factors explain my preferences in movies? That's what we're trying to get at. Another way to think about what we're doing here is it's very much like factor analysis. So factor analysis, remember, identifies these unmeasurable latent factors that explain the X's that we've observed. So this is like factor analysis, but we have a very sparse matrix, whereas the factor analysis that we studied earlier assumes a complete matrix. I'll just mention that information retrieval has had similar issues, and they've come up with methods like latent semantic indexing that identifies concepts that explain what's part of a document. And these concepts are kind of at a higher level than just mere words. Words we can observe, but concepts have to be inferred by the words that are part of this. They're latent ideas, just like factor analysis. The solution we're going to find is to take our ratings matrix. So here's a ratings matrix. So notice my ratings matrix does have a few missing entries. Of course, in practice, there'd be lots of missing entries in this. We're going to decompose this rating matrix into two parts. So the two parts are taste vectors and loadings. So we're going to have one row in this taste matrix for every user, and then we're going to have k columns in there which indicate these, whatever you want to call them. You can think of them as latent factors, like factor analysis, or you could think of them as concepts, as we had with latent semantic indexing. But these are going to be, k dimensions that explain my tastes. Now the loading matrix is going to have one column for every item. So here I had 5 items, so there's going to be 5 columns in this matrix, and it will have one row for the value of that item on that dimension. You could think about what we're doing is really similar to content-based filtering, where, for example, I have action versus romance, and those are genres that I can agree on with you that exist for these movies. And think of this as your user profile. So this taste matrix is analogous to a user profile. This first row is going to say how much does my first user like comedies, so if the first column is comedy, versus romance. This is how much the first user likes romance. This is how much the second user likes comedy versus romance. Our interpretation of the loading vectors would be, this is the extent to which movie 1 is a comedy. This is the extent to which movie 1 is romance. You could think of having both in there, or one, or neither. This is going to be how much movie 2 has comedy, and this is how much movie 2 has romance. Think of this as the item profiles in content-based filtering. The only difference is, rather than having some attribute that we can agree on, these are going to be latent attributes that are discovered by the machine learning algorithm. So as an example, how much is user 3 going to like movie 2? You'll see that that hasn't been provided. Well, the way we do this is we say that's going to be, so how much does user 3 like comedy times the amount of comedy in movie 2 plus, well, how much does user 3 like romance times, well, how much does movie 2 have romance in it? So if I do that dot product, I get a prediction of how much user 3 is going to like movie 2. So remember how I said it's computationally very difficult to compute ratings using user-based collaborative filtering or even item-based collaborative filtering. To get predicted ratings here is dead simple. It's just an inner product that is computationally of order k, so the number of taste vectors that I have. Well, how do I estimate my taste and loading vectors? That's a very important question. One approach would be minimize the sum of squared errors, just like we did with regression. You can think of that's what we were doing with principal components analysis as well. Just minimize the sum of squared errors. We can express that with what's called the Frobenius norm. So the Frobenius norm just says, well, add up the sum of squared errors in this matrix, and we're going to make that as small as possible. So there's our objective function. This turns out to be a very difficult problem, though, numerically. I warned you about this with factor analysis. Factor analysis is not a simple problem to estimate, and the history of factor analysis estimation routines is quite extensive. So originally people used principal components, which were reduced to an eigenvector problem, and that wasn't too bad, but that wasn't really estimating the factor analysis model. Then various simplified versions came around, so squared multiple correlations and other methods, which are still available in software today, were proposed. Then finally they figured out how to do maximum likelihood estimation. We have the same difficulty here. And so what we're going to find is there's a lot of different ways of estimating these taste and loading vectors. Before I get to estimation, let's do another example of this. Suppose I have 6 items. So these are different movies. This is going to sound a lot like content-based filtering, where some of these are about history and some of these are about romance and some are actually about both. The difference is history and romance are not attributes that we decided on ahead of time. History and romance are these latent factors that were discovered by our estimation routine. Let's say here is the taste matrix and the loading matrix. What I'd like to point out here is, okay, Nero is just about history, so history is a 1. It's not about romance. There's no romance in Nero. Whereas we can see Cleopatra has both, while Sleepless in Seattle is not at all about history, but it is about romance. Likewise with Pretty Woman and Casablanca. So here we have our loading matrix, which is describing these items on the latent factors. Now, suppose we have these, what do I have here? 7 users, and user number 1, you can see, loves history, is not into romance. So then the question is, what will user number 1 like in terms of these movies? Well, if we do our inner product, we can see user 1 is going to like Nero, user 1 will like Caesar, and user 1 will also like Cleopatra. User 1 is not going to like any of the other 3 movies because they don't have any history in them. Let's go look at another user. This particular user you see actually hates history. If history is in it, that user is not interested. But this user really likes romance. So we can see that this user would actually have negative utility for Nero and Caesar, but we would expect 0 utility for Cleopatra because there's a little bit of history and a bit of romance in there. I said these are approximately equal, so this guy actually hates Cleopatra, but we would expect this person to be kind of neutral about that, whereas this person should love the last 4 movies because they're only about romance without history. Well, let's turn to the question of estimation now. There are a lot of different ways that we can estimate T&L, and nobody has really decided which one is best. The simplest approach is to use the singular value decomposition that we talked about with principal components analysis last year. As a quick review, the singular value decomposition of some matrix R is going to be a product of 3 matrices, so P, sigma, and Q transpose. So we can go look at what this would look like. If this is an N by P ratings matrix, so I have N rows, we're going to have K columns. So this is going to be an N by K matrix, which we could call, we called P last year when we were doing the SVD. Then we multiply that by this sigma matrix. Sigma is a diagonal matrix, so this is diagonal. So these have the square root of the eigenvalues from principal components analysis. They're called singular values along the diagonal. And remember, these had a very important property. The larger the value, the more variance was explained by that item. And so we usually sort these from the largest singular value to the smallest singular value. And then we have this Q transpose matrix, which is going to be K. This is K by K. This is K by P after you've transposed Q. So Q would be P by K. And so, wow, this looks a lot like what we have, what we need to make our taste and loading vectors. So here's the idea. We're going to not keep all of the dimensions, because if we keep all of the dimensions, we will overfit the data. So I'm going to select K star, strictly less than the K that I was sketching out, dimensions. This is going to be one of the tuning parameters for this model. So the more taste vectors I have, the better I'm able to describe your tastes, but I don't want to over-explain your tastes. So this is going to be one of those factors that we're going to have to choose through cross-validation or a test set. We immediately have a problem because the singular value decomposition is only defined when all of the values in R have been observed, and there's a whole lot of missing values. We saw some here. In real life, of course, there might be 99% of the values might be missing. So what do we do? Well, we can do a number of things. We could just impute the item's average rating. We could normalize the ratings. This would be by row, so by users, if you will, and then impute zero. So this would be the user average. And this has another benefit of taking out biases in the way that different users use the scale. The textbook that we're using, LRU, gives another method which shows us how we can minimize these errors for only the values that we've observed, and we will not enter in any unobserved combinations into our objective function. So we would be minimizing the sum of squared errors across all the observed ratings. This cell, and this cell would not enter into my objective function down here. Now, another problem that we're going to have is that SVD itself is not that easy to compute. And the estimation can take a lot of time, especially when you have a large rating matrix. So what's been proposed is a method that I'm not going to talk about in this class, but you may have encountered it in another one of your machine learning classes called stochastic gradient descent. So gradient descent provides a way to minimize some objective function like the Frobenius norm. Stochastic gradient descent draws a sample of observations to speed things up, to compute the gradient. So we're trying to minimize this thing. We're going to take hops along the gradient. The gradient shows which way is down. We can compute that gradient using just a sample of data, and that speeds things up. So that's another approach that will get used. So there are a lot of different variations of how to estimate this. So one of them, which is available in both R and Python, is called alternating least squares. Instead of finding the SVD, what we do with ALS is to switch between estimating T with L constant and then estimating L with T constant. So it's a little bit like what we did with k-means, where with k-means we fixed the cluster centers. And once you do that, it's fairly easy to assign observations to the nearest centroid. Having done that, we fix the assignments and recompute the means. So the way k-means worked was to alternate between those two things. We're doing something very similar with alternating least squares, where we hold one of the things constant, which makes finding the other part fairly easy. Another approach is called biased matrix factorization. The idea of biased matrix factorization is that we want to estimate user biases within the algorithm itself. And of course, this is going to add a ton of parameters that have to be estimated. What we're going to find is that this biased matrix factorization is a very slow algorithm, especially if your ratings matrix is large. But it's also going to be a pretty good one because it's taking care of these user biases at the same time. So this might be better than what I proposed on the previous slide, which was to normalize your ratings first and then impute zeros. That's kind of taking the biases out as well. Ultimately, you want to test these things. So this method and others are described in a very famous article that I encourage you to look through, which is this Corin article. So Corin was studying the Netflix challenge. So Netflix had offered $1 million bounty to any team that could improve the RMSE of the recommendations by a certain amount. And so what you'll see in here is an example illustrating just what I said. So you could have two latent dimensions, which is serious versus escapist. So Amadeus is a very serious movie, whereas, say, The Lion King or The Princess Diary is very escapist. Then you have movies that are sort of geared towards males versus females. So Dumb and Dumber is very much geared towards males, whereas something like Sense and Sensibility or The Color Purple would be more geared towards females. And you could then position these within that space. You can also position users in the same space. So what I'm plotting here is really the loadings. So this would be like my loading matrix, and these are all my items plotted in that two-dimensional space. I could stick users in the same space because I'm describing them in my taste matrix on the same two dimensions, and then just look for which movies are closest to an individual. That's basically what's happening. If we go on, we can see an actual plot that they generated using the Netflix data. And here we have these latent factors that really haven't been interpreted, but they position movies in this space. And so we can say that Citizen Kane and Annie Hall are quite similar, but they're very different than Half-Baked or Coyote Ugly. So Coyote Ugly is very different than Citizen Kane, and so forth. You can come down and see how the different algorithms do with on RMSE as a function of the number of parameters. So if we use basic matrix decomposition, RMSE is quite a bit higher. Once we bring in those biases, it goes down, but we have more parameters. They have some additional methods that take into consideration temporal dynamics that reduce RMSE further. There are some other decompositions that we don't really have time to get into. You can read about them on the Wikipedia page, though, if you have interest. What I'd recommend is that you try these algorithms. They're available in software. Set aside a test set and see which one performs better. We've already seen that in some of my other videos where I was comparing, for example, the SVD method with user-based collaborative filtering and popular, and so forth. Here's a few things to keep in mind about NMF. So it's very good for unary data where I don't have ratings. And when the set of liked items is pretty small in the entire catalog. So I'll close with a few big takeaways. So the dimensionality reduction methods are clever and useful. They have real computational advantages, especially at runtime. Estimating the models can be difficult. I'd say that they're growing in use, but they're not dominant. And finally, this is a very active area of research, and people are still working to improve these methods, as well as other methods, including things like deep learning neural networks for recommender systems.